Ah, premessa, siccome sono delle lezioni che le usiamo anche per una scuola al GGI, ripeto la parte sulla Lagrangiana di QCD perché era prevista che lo facessi in quella lezione. Ok? So, welcome everybody, and today's lecture is devoted to the study of jet quenching in the ion collision. So, maybe before addressing the technical topics, it's better to understand what's the philosophy of this kind of approach to get some knowledge on the matter produced in a ion collision. So we are toward the end of the class on the study of heavy ion collision, so you should have sufficiently clear in mind this picture, which is a space-time cartoon of the evolution of the matter produced in heavy ion collision. Z clearly is the collision axis, and this is time. So you have two nuclei which collide, moving along the light cone practically at the speed of light. And so essentially the two nuclei are essentially transparent and carry away essentially all the baryon number, and what remains here is some excited matter, which at the beginning will be in a para-equilibrium stage. Then there is quite a strong evidence that very rapidly, in less than 1 Fermi over C, the matter goes close to local thermal equilibrium, and so on, and undergoes a hydrodynamic expansion, quite well described by viscous hydrodynamic calculations, and it lives for a certain time around clearly depending on the centrality of the collision, but let us say around 10 Fermi over C. The matter spend part of its lifetime in this quark-gluon plasma phase. Then it cools down, it hadronizes. There is a stage of hadron gas in which hadrons still rescatter a bit, and then you reach a freeze-out temperature, after which the hadrons reach the detectors. So the philosophy of the study of hard probes, which are particles produced in hard processes, and they can be IPT partons, they can be heavy quarks, or they can be quarkonia. So they are particles which are characterized by a hard scale, which can be either the PT or the mass or both, so that the production occurs in the very beginning, and so essentially they are produced at the initial stage, and before reaching the detector they cross this the confined matter. And this, the idea is to compare what happens in nucleus and to what happens in proton-proton collisions, in which the initial condition, the initial production, you expect to be the same because it's a hard process, it's a short distance process, but the difference is that you don't have this stage in between, so you expect observables to be modified. Okay, so which are these observables? Because here I wrote the title jet quenching, but actually for many years people essentially simply study the spectra of charged particles, of charged hadrons in particular, since at the beginning detectors were not conceived to study jets. So some of the detectors used in heavy ion collision don't have a full coverage of by calorimeters, which are necessary for the study of jets. Then there is also the issue of developing proper jet finding algorithms to identify jets in a very complicated environment with thousands of charged tracks. And then there is also the issue that at the beginning, in the center of mass energy in first heavy ion experiments was not so high to have an abundant production of jets. Okay, so essentially, as I said yesterday, the study of the quenching of IPT particles was carried out looking at this observable, which was essentially the ratio between the PT spectrum in nucleus over the same spectrum of particles, pions, protons, kaons, charged hadrons in proton-proton times the number of binary collisions, okay? Binary nucleon-nucleon collisions, okay? So in particular, if for this you obtain a result less than 1, you can infer that there is some energy loss in the medium. So let us look at experimental data just to check what I'm discussing. Let us go forward. And so this is an example. These are experimental data by the Phoenix experiment, in which you see you have this quantity RAA as a function of PT. Notice that this was an experiment at 200 GeV center of mass energy, so at the beginning you didn't reach so large PT. These are photons, and photons once produced are not affected by the medium because they don't have color charge. In fact, their RAA is compatible with 1. These are hadrons, they are pi 0 and eta, so I suspect that the measurement was performed with some electromagnetic calorimeter. So you see the ratio is very small, is around 0.2, okay? So you have a strong suppression, and the fact that for photon and this ratio is 1, it means that it is a final state effect. It's not an initial state effect due to, for instance, assuming that parton distribution function in nuclei are dramatically different with respect to parton distribution functions in proton-proton. Okay. Okay, there are some differences. They can be studied by doing deep inelastic experiments on nuclei, but they are not the explanation of this result. This is the same, but LHC. You see, these were the first results by Ellis, this time for charged hadrons. Different centralities from more peripheral to more central. You see that the center of mass energy was 2.76 TeV, so you could reach larger transverse momentum. And you see again this dramatic suppression, and also this trend of having less suppression of in the spectra going to larger PT. Of course, notice that the scale actually is logarithmic, so this region is a bit overemphasized. This is the same for CMS, in which okay, they managed to go to larger transverse momentum, and again they performed this comparison with electromagnetic probe. This is the RAA of isolated photons, again compatible with 1, while for charged hadrons you have this suppression. These are the most recent results. You see they managed to go up to 400, almost 400 GeV in PT. These are charged hadrons. This is the situation in nucleus. You see that you have this rise in the RAA that we will try to explain, and this is as a further comparison. This is the situation in proton nucleus, where again you see that it is essentially compatible with one, okay? At least in the region in which you expect that the production scale with the number of binary collisions. So all this tell us that this quenching is a final state effect. And now let us move to jets, because so far these were charged hadrons. And these plots were the result of a offline analysis, okay? But look, the surprise was to discover the performance of LHC detectors to really study jets, and also looking at very nice effects just looking by eye at the event display. So this is, for instance, one of the first lead-lead collisions measured by Atlas, which has a full coverage hadron calorimeter. You see this calorimeter is segmented in the azimuthal and polar angle. This eta is the pseudo rapidity, so it is essentially related to the cosinus of theta. Theta is the polar angle, and you see you have this sort of very unbalanced, or almost, they looks like a monojet event, okay? But the point is that you should have something on the away side. You don't see anything, not because you have produced some particle flow into some extra dimensions, but because the companion lost its energy in the medium, okay? This is again by CMS, another unbalanced dijet event. You see you have a leading jet of a PT of 200 GeV and a subleading jet with PT 70 GeV. So the companion has lost a lot of energy in the medium, okay? Of course, then you should try to do your study more quantitative. And the way to do this is to introduce some asymmetry variable to study this dijet unbalanced. And this asymmetry variable was introduced by Atlas, I think, to remember, which they introduced this variable, which is essentially the imbalance in transverse energy of the two jets with respect to the sum. And clearly it is 0 if the jets are exactly balanced, and it is large if it is not balanced. Okay, and what do you see here? So essentially then events where people study the distribution of events with respect to this variable, going from more peripheral events to more central events. And you should check the experimental point with the proton-proton data, okay, at the same energy. Actually, at that time, they didn't have proton-proton data exactly at the same energy, so they had to do some Monte Carlo to interpolate between energies for which data were available. But in any case, you see that nowadays there are reference data at the same energy, but this situation has not changed. But in any case, what you see is that going from a more peripheral to more central event, you find an excess of unbalanced dijets, okay? You see this is nucleus-nucleus in black, and the proton-proton reference is in white, so the empty bullet, okay? While you do the same looking at the relative angle of the two dijets, and you don't see such a strong effect with concerning the relative angle. They tend to be back-to-back in azimuth, except for this tails, which in any case contains just a few events, okay? So that's all for what concerns phenomenology. Now we must build the tools to interpret these results, okay? So in particular, we want to provide an interpretation in terms of QCD. So I start by reminding you how to build the QCD Lagrangian, also because we will need the Feynman rules to calculate the Feynman diagrams. So we start from the free quark Lagrangian, which is diagonal in the flavor f of the quarks, and in particular the quark field, let us consider an up quark, can be considered as a vector with 3 components corresponding to the 3 colors of the quark, red, green, and blue, for instance. And this Lagrangian, from the point of view of color, as a global, written as it appears now, as a global SU3 invariance. So it means that I can rotate the quark field by a SU3 matrix, so a unitary matrix with determinant 1. I rotate both the quark and the q-bar field with parameters which are constant, which they don't depend on the space-time point, and these sub-matrices and are the generators of the corresponding SU3 algebra, and so which is defined here. It is defined in terms of this structure constant, which are real antisymmetric numbers. Okay, there are nc square minus 1 generators of this group, and that's all. Now we would like to make this invariance local. So we would like that this Lagrangian remains invariant even when the transformation depends on the space-time point. So even when these parameters, these real parameters, these angles, depends on the space-time point. Of course, since here there is a derivative, as such the Lagrangian is not invariant, because the derivative can also act on this matrix which describes the rotation in color space. In fact, if I apply the transformation, the free Lagrangian gets in its transformed form this additional term. So what's the trick? The trick is the following. Since problems came from the derivative, I modified the definition of the derivative, and I introduced a covariant derivative defined in a way, in a proper way, in order to cancel this extra term. So the derivative is promoted to a covariant derivative, which is in which one introduced this further field, which is a gauge field. It has a matrix structure, so it is written in terms of the generator of a SU3 group. And now the Lagrangian for the matter part, so for the quark part, has an additional term, which is this term, which comes from this additional term in the covariant derivative. So clearly now I can define a transformation law for this a mu field in such a way to compensate for this extra term coming from the transformation law of the quark field. And the trick to do so is to make this field transform in such a way. So you see that this piece ensures that this object remains invariant, because the V dagger from this transformation cancels with the V from this transformation, the V from this transformation cancels with the V dagger from this transformation. But this additional term placed here cancel this one. Okay, so you can verify that the Lagrangian for what concerns the quark sector is now invariant under local gauge transformation. In particular, you realize that the covariant derivative applied to the quark field transform as the quark field itself. And this means that since the transformation law for the quark field is V multiplying Q, it means that the covariant derivative must transform in such a way. And this will be important just in the following, in order to define also a proper field strength of the gauge field, because now what we are left is to introduce a Lagrangian also for this gauge field, because if I stop here, this is just a background field, but I want to introduce also a Lagrangian for this gauge field. And the trick is to exploit the analogy with QED, which the QED Lagrangian is written here. The field strength is this usual definition. Remember that in QED the covariant derivative is defined in such a way, with this different sign with respect to the QCD, just for convention. Now you can check that from this definition of the covariant derivative, F mu, the field strength in QCD, can be written in such a way. Okay, of course this is a formal way of writing. You must imagine to apply this object to some trial function, and you see that if you expand this commutator, you get exactly this definition. But now, which is the advantage, is that in such a way the generalization to QCD is straightforward. You have simply to change the definition here of the covariant derivative, and correct here, instead of minus I over E, you put plus I, because this due to this change, difference in sign over G, which is the strong coupling. Now there is a difference, however. Now the group is no longer abelian, because the QED is based on the U1 group, which is abelian. QCD is based on SU3 group, which is not abelian. So in particular, while in QCD the term A mu commutator A nu is 0, here, since they contain color matrices, this commutator is no longer 0. And if I write explicitly the fields in terms of their color components, what I get is the following. Okay. In particular, from this and from the transformation law of the covariant derivative, you get that F mu nu is not invariant. So this would mean that if I write simply an expression like this one, I would get something not gauge invariant. But the trick is to insert a trace, and the cyclic properties of the trace make this definition gauge invariant, because now the V from here is cancelled from the V dagger from here, which I can put at the beginning. Okay. Now, if you employ this normalization condition for the SU3 matrices, for the trace of two SU3 matrices, you get this expression, which is very similar to the QED1, except for this color indices. Now, this is the QCD Lagrangian. What matters now is the Feynman rule in order to perform perturbative calculation. Feynman rules are the ones for the quark, for the gluon propagator, which clearly will depend its explicit form, its explicit tensor structure will depend on the gauge that we choose. This is written in the Feynman gauge. You get a further Feynman rule for the quark gluon vertex, in which you see I wrote explicitly the color indices to show that this vertex describes a color rotation of the quark. Okay, this matrix take a quark with a color index J and rotates it to a quark with a color index I. Okay, and then since you have also this non-abelian term, you have also in QCD a 3-gluon and a 4-gluon vertex. And we will focus on the 3-gluon vertex, which will be the one relevant for our studies, which has this Feynman rule. And you see, since clearly F mu nu, you see that it will have a structure, the mu A times AA. So the presence of this derivative entails that the vertex has a momentum dependence. Okay. Now, let us now move to some color algebra. Quark rotations in color space are described by these matrices, which are NC times NC matrices, so in NC equal to 3 in QCD, which belongs to the fundamental representation of SU and C. On the other hand, color rotation of gluons, like in this process, are described by NC square minus 1 times NC square minus 1 matrices, TA, which are again matrices of the SU3 group, but which belong to the adjoint representation. So, how can one define the adjoint representation? Well, the adjoint representation is the one in which the matrix elements of the matrices coincides with the structure constant of the algebra, okay? And this you can verify very easily. So if you don't believe, substitute this definition into this which is the definition of the SU3 algebra, and check that this identity satisfies, so that this is actually a representation of the SU3 or SUN algebra. And the trick is to exploit the trivial Jacobi identity, in which I take this nested commutator, in which I perform a cyclic permutation of the indices, and this is you verify that it is 0. This entails a relation between the structure constant, which are useful to verify this identity. But now, which is the advantage? The advantage is that now I can view also this 3-gluon vertex, which was written in terms of this structure constant, as a rotation in color space. So I can imagine it to describe the rotation to the emission of a gluon of color A, of a gluon which initially had the color C and is rotated to a gluon with color B. Okay? I can also use some graphical shortcut to evaluate explicitly color factors, and this shortcut are based on these graphical rules, which are exact in the large NC limit, in which I can identify a quark line by simply a line with an arrow, and then a gluon can be identified with a quark anti-quark line. Of course, this is not completely correct, because in this such a way I would have NC square gluons, while in reality I have NC square minus 1 gluons. Okay, so there are corrections to this picture which I could insert. I could have drawn some other diagram here which compensate, but for simplicity, since in many cases we will work in the large NC limit, I have decided to adopt a simpler approach. And now I will show you how this is useful to evaluate color factors. So the radiation vertices are given by these rules. So you see that this is the radiation of a gluon from a quark, and you see it's very easy to draw the process. Now, in the case of a radiation of a gluon from a gluon, you see that I have two different choices, because I can decide either to attach the radiated gluon to the quark line, or the radiated gluon to the anti-quark line. Okay? And I have here a minus sign, because the anti-quark has an opposite charge with respect to a quark. Okay? Well, this immediately tells me that I can get very easily color factors, because you see that let us, for instance, consider the radiation from a quark. You know from the optical theorem that this can be obtained from the cutting rules, if you wish, from taking the imaginary part of this self-energy, okay, which if I have TA, this self-energy would entail the calculation of this quantity, which is the Casimir of the fundamental representation times the identity matrix, and this Casimir is nc square minus 1 over 2 nc. Okay. Now let us imagine to evaluate the same, but from within this picture. So within this picture, I have the following. And you see, if I identify the color indices, what do I get? I get a factor 1 over square root of 2, 1 over square root of 2, and then I get a factor nc from this this loop, because here I can have nc different colors which can flow. So the result is nc over 2, which is exactly the large nc limit of this expression. Okay. This tells also me that the radiation probability from a gluon is 2 times larger than the radiation probability for a quark line. And I invite you to check, to do the same with this diagram. You will discover that in the large NC limit, you would get a factor NC over 2 from the square of this, a further factor NC over 2 from the square of this, and the cross terms are subleading in the large NC limit, because you will not be able to draw a closed loop which gives you a factor NC. Okay. And so physically it means that I have a double probability, simply because I can radiate either from the quark line or from the anti-quark line. So now we will discuss a bit QCD in elementary collision. So in particular, we will what we will be interested in is not really the evaluation of the hard process, but the evaluation of the shower. Okay, so the evaluation of the probability of radiation of soft gluons before or after the hard event. Okay, and then what we will do will be to generalize these techniques to discuss the case in this in which this gluon radiation occurs in the presence of a medium. So in most of our calculation, we will work in light cone coordinate, which so in cosine coordinate, you know, you have a 0 component and a 3 special component, and A dot B is calculated with this metric tensor. While light cone coordinates, you introduce a plus or minus component of a 4 vector defined in such a way, and you can verify that the scalar product of 2 4 vectors is evaluated in such a way. So the metric tensor is off diagonal. Okay, so you have a matrix tensor which is something like 0 0 1 1 minus 1 minus 1. If this if you label the components in such a way. Okay. Check, but this will allows us to perform a calculation in a quite fast and convenient way. So essentially what I will focus now is the evaluation of the probability of radiation of soft gluons from some high energy virtual parton produced in some hard event, which I don't even know exactly what it was. Okay, so I imagine to start with some initial parton with some large virtuality, okay, and zero transverse momentum. So I decide that these partons propagate along the z-axis, and you see that if I parameterize you see that in this case I would have pi square. From this metric tensor I get 2p plus q square over 2p plus, okay, the q square is the virtuality of the initial parton. The final state parton on the other end are assumed to be on shell, so this gluon radiation was sufficient to put these two partons on shell, and in fact you apply this same definition of the square for vector. Here you would get 2x p plus divided by 2x p plus times k perp square minus k perp square. So this gluon is on shell. Also this final state quark is on shell. Transverse momentum is conserved, and furthermore you see that you have that k dot epsilon is equal to 0. Okay, this the gluon which you radiate is transverse. In fact, take the scalar product and you get this result. Okay, can you see it? Okay, now let us evaluate this result. Let us evaluate this radiation amplitude. So let us apply Feynman rules. This is very general. You have the spinor, then you have Ig tie A from this vertex, then you have epsilon slash from the contraction. Well, actually here there should be a star, but I will take its component as real. But in any case, okay, there should be a star, but it's not so important. I have the quark propagator, and then I have the matrix. I have the amplitude of the hard process. Okay, now in the soft approximation, it means that I assume that the gluon carries away a small fraction of energy. I can neglect this k slash, and now what's important? This is very general. I mean, now exploit the anticommutator rules for the Dirac matrices. So it means that you can write epsilon slash p slash final like 2 pf dot epsilon the polarization vector of the gluon from this 2g mu nu minus the term in which I have exchanged the order of the two, p slash epsilon slash. But what's the point is that now this multiplies directly is multiplied directly by this final state spinor, and due to the Dirac equation this is 0, and so at the end we are left in this soft limit with this result. So this is very important. You have this G from the coupling, this TA from the color matrix, this universal factor times this amplitude for the hard process. And you see, no matter what the hard process was, this formula always holds, and does not even depend on the spin of the radiator. In fact, this is a classical result actually, but it depends only on its color charge. So if the radiator were a gluon, I should simply exchange this matrix in the fundamental with a matrix in the adjoint. Okay? So I can also decide, since in the following maybe we'll have to perform some complicated calculation. One can even decide to get rid of all this Dirac algebra and work with scalar quarks, and one would obtain this same effective Feynman rules, which verify with this effective Lagrangian for the quark. You get this directly this expression, okay, which is an expression which would lead you to exactly this formula. This is the iconal approximation. Maybe you have already seen sometimes, and you see that you have this perfect symmetry also with the gluon. Okay, you have 2p plus k, and okay, collecting a factor -2, you have again also here 2p plus k. Okay, then this plus k, once you contract with epsilon, is no longer important, but okay, formally it is there. Okay, so one gets this now that one gets this result. Let us try to derive this formula for a moment. So let us try to perform explicitly the calculation, since it will be one of the most important formulae we try to derive explicitly. Then you understand how things are done, and you can trust other formulas in the following. So we have Pf, which is equal to 1 minus x times p plus. Then you have k square over 2 1 minus x p plus, and then you add minus k perp. Okay, don't put I assume that all these vectors are vectors in the transverse plane. Okay, if I forget, don't pay too much attention. Then now epsilon of the gluon is equal to, I choose to work in the light cone gauge, in which the plus component is 0. Now, once I perform finally there is also k, which is equal to x p plus k square over 2x p plus, and then there is k perp. Now let us perform calculations. Pf dot epsilon is equal to, okay, this times this is 0. I'm left just with this times this, so I'm left with 1 minus x over x. P plus cancels, and I get epsilon dot k. Then I get minus, but here I get a plus epsilon dot k. Correct me if I do something wrong. So I collect a factor 1 over x, and I get epsilon dot k over x. Then I would get minus x epsilon dot k plus x epsilon dot k. Okay, now what I have to calculate is also pf dot k, and pf dot k is equal to 1 minus x over x, p plus cancel, and I get k square. Then I get a plus, a further plus. There is a factor 2, if I'm not wrong. Then I get this with this, and I get x over 2, 1 minus x. K per square, and plus k per square. So I am left with, let me go here, so I have 1 minus x square times, so I have everywhere I have a k per square, and then I have 1 minus x square plus x square plus 2 1 minus x times x. Okay, but this is nothing but I can rewrite it as 1 minus x plus x square, so this is 1 divided by 2 times x, 1 minus x. Okay, k square. Then if I do things correctly, I should get this result. Okay, now in order to evaluate this cross section, you must take the square and sum over the polarization. Once you do this, if you sum over all physical polarization, this factor produces this sum produces a factor delta ij, this sum over polarization, which makes this, from the square of this quantity, you get k square over k to the fourth, so you get 1 over k square. Okay, then you must also integrate over the phase space of the radiated gluon, and remember that you can write d3k over so d3k sorry, no sorry, dn over d3k times k times e of k, you can write as dn over dy the 2k perp, where this dy you can write as the k plus over k plus. Okay, so that's the reason of the origin of this expression. So now let us interpret this expression, which was obtained in the limit of a soft gluon radiation. You have the cross section for the hard process times alpha s, which comes from the g square. Then and then you have 1 over k perp square, which comes from this radiation vertex, and then you get this, which comes from the phase space integration. Okay, at the end, what the important thing to notice, does it work? See, the important thing to notice is that, as already seen in the lecture on on the color glass condensate is that the spectrum is both infrared here and collinear divergent. Okay, so I have an infinite probability to radiate a gluon very collinear, parallel with the initial parton, or carrying an infinitesimal fraction of its energy. Okay, so this is actually not really important in the sense that in any case, at the end, what you measure are hadrons. So in any case, in a parton shower, you have to decide a minimal scale below which you have to make a transition between hadrons, between partons and hadrons, and you must perform hadronization, which has to be modeled somewhere. Okay. Then the last important point, the other two important points to notice is that you have a link between the transverse momentum of the radiated gluon and the virtuality of the initial parton. So the larger the virtuality of the initial parton, the larger the transverse momentum of this radiated gluon, and this you can simply obtain by imposing momentum conservation. You see that from here you get that q square over 2p plus is equal to, so the minus component must be conserved, is equal to k perp square over 2x p plus k perp square over 2 y minus x p plus, then clearly p plus cancels, and okay, if you do calculation correctly, you get, of course, you see immediately that in the soft limit, this is the most important term, because you have this 1 over x enhancement, okay, which while this is not enhancement for soft gluons, it's not enhancement for soft gluons. In any case, if you do things correctly, you get this result, okay. And then last point is that you have also a formation time for this radiated gluon. So you can ask how far from the hard event on average this gluon will be radiated. Clearly this is not relevant in the case of a parton shower developing in the vacuum, but it can be relevant for a parton shower developing in the medium, because in the case of a medium you have a certain physical scale to which you can compare this formation time. Okay, these formation times can be estimated simply by assuming that it's proportional to the inverse of the virtuality, but this is the formation time in the rest frame of this parton, and then you must boost by this gamma factor, where so this is like considering it as the mass of the parton, the virtual mass of the parton. So this is a gamma factor, and so if you substitute now, so you see that this formation time now is equal to 2 omega over k perp square. So substitute here for the virtuality, substitute this result, and take into account that x is omega over the energy. Omega is the energy of the gluon, E is the energy of the initial parton of the radiator, and you see that this formation time has this expression. And now, since k perp is omega times theta, okay, for small angles, okay, then you see that in practice this so this k perp for if this is the energy of the gluon, k perp for small angles is approximately omega times theta. So it means that this omega over k perp square is actually something like 1 over omega theta square. Okay, so soft and collinear gluons have a very long formation time. Okay, you see, so the dependency is since this k perp square is equal to omega square theta square, you get these results. So softer and collinear gluons are emitted later in a Barton shower. Okay, now let us go to a further point, which is the discussion of color coherence. So we have seen that the radiation of long wavelength gluon is not sensitive to the short distance details like the spin of the radiator, but only on the total charge of the emitter. And so this will have importance also to understand the angular distribution of the radiation. So for instance, maybe you have seen this in some PQCD classes. You have some, let us assume we have some color singlet emitter which splits into a QQ bar pair. This can be a photon, can be a X boson, can be a Z boson, can be a W, can be anything. And let us consider the gluon radiation from these legs. Of course, I can radiate either from the quark leg or from the anti-quark leg. Okay. Pay attention that here I have labeled the momenta in the correct way as they appear in the propagators. Okay. So if I employ these effective soft gluon vertices, I get this result for the amplitude. Okay, we have derived this result previously. You have simply here a difference, this minus sign, because in this case you emit from an anti-quark which has an opposite color charge. Now, in order to evaluate the radiation cross section, you must square the amplitude and then sum over the polarization of the radiated gluon. You can, for instance, this time let us, for instance, decide to work in the Feynman gauge. Well, in the Feynman gauge, this sum over the polarization of the gluon produces this factor minus g mu nu. Okay, and one gets then what one has to do. One has to take the square, sum over the polarization, and this fact that the fact that there is this minus g mu nu tells me that I must square this, but I get a p square from this, which is a 0 because this quark is massless. I get a p bar square from here, which is a 0 because the quark is massless. I get just the contribution from the double product with the minus sign cancelling this minus sign. So I get a structure like p dot p bar, and the denominator p dot k, p bar dot k. Okay, I get this structure. Then I integrate over the phase space of the radiated gluon. I get this factor CF from the square of this color matrix, g square from the vertex, and that's all. Now, you can explicitly write both the phase space integral, okay, here, and you can explicitly write this term in terms of the relative polar angles of the particles. And you get this expression where clearly this is the opening angle of the initial QQ bar pair. This is the relative angle between the radiated gluon and the quark. This is the relative angle between the radiated gluon and the anti-quark. Okay? And now one would like to provide a probabilistic interpretation so that I can insert this kind of stuff in some event generator which are based on some Monte Carlo technique. Clearly, the issue is not non-trivial, because we have seen, for instance, in this gauge, the result comes entirely from the interference term. So how to put an interference term in a probabilistic setup is non-trivial. However, one can perform some trick. So for instance, one can write this object as a sum of two different objects defined in this way. And the important point is that, let us focus for instance on the first one, is that for instance these two terms will be enhanced in a completely different regions of phase space. So for instance, this term will have a collinear singularity for gluon radiated very collinear with respect to the quark, while it will provide a finite small result once the gluon is emitted collinear with the anti-quark, and vice versa. This other term will have a collinear enhancement in the case that the gluon is emitted collinearly with the anti-quark. Okay? If you decide to be less inclusive and take an azimuthal average, the result is really exact. So after azimuthal average, you get that the first contribution comes just from gluons which are emitted so if this is the quark and this is the radiated gluon, this radiated gluon, the first term will be forced to be emitted within this cone obtained by making the opposite charge rotating with respect to the radiator, and vice versa. This other gluon will be forced to be emitted in this other cone. Okay? So at the end, this is the formula that you get, and which tells you, this is called angular ordering of vacuum radiation, and it tells you that in QCD you tend to produce jets, so collimated spray of particles. You can also try to give a probabilistic interpretation, and in terms of formation time. So remember that the formation time for gluon radiation was of this order, of omega over k perp square, which means 1 over omega theta square. Okay? Now the point is that the transverse wavelength of the gluon, so lambda perp is the inverse of k perp, so it is the inverse of omega theta, the angle of the gluon, must be sufficiently small to resolve the transverse separation reached meanwhile during this formation time by the quark and the anti-quark, because otherwise they would be seen as a color neutral object. Okay? So if you apply this condition that the transverse wavelength be smaller than the transverse separation, you get this condition for the angle, the energy cancels, and you get that the angle at which the gluon is radiated must be smaller than the opening angle of the antenna. Okay, so you've seen the same things just from a qualitative argument. Okay, so this is the result. The result is that in high energy collisions, particles are not distributed isotropically, but they tend to be produced in collimated structures, which are called jets. Okay, and these jets are the object that will be quenched in nucleus-nucleus collisions. You can, I mean, this has also consequences for the distribution of particles within a given jet. This, for instance, is how particles are distributed according to the momentum fraction they carry of the jets. So this is the momentum of the hadron divided by the jet energy, and with this definition, here you have soft particles and here you have hard particles. and applying the same considerations that the radiated gluons must be able to resolve the color charges of the antenna, and considering that the transverse momentum of the radiated gluons must be larger than lambda QCD, you get a constraint for the energy of the radiated gluons, which translates in a constraint on the energy of the final state hadron. So this provides you a suppression of a very soft hadron production within a jet. Okay, with respect to what you would expect just on a phase space argument. Okay, this is called the unbacked plateau. And then finally, you have also some nice consideration between the angular pattern of particles produced outside the jets. And for instance, consider these were studies performed at CLEP in E plus E minus collisions, in which you had E plus E minus, a virtual photon, and in general two opposite QQ bar pairs. And these QQ bar pairs can also radiate either gluons or photons, and you can select event with exactly the same kinematics. The only difference is that in this case you have a gluon, in this case you have a photon. Okay, the point is that in this case you would have a three-jet event. In this case you would have a two-jet event plus a hard photon. But if you look at how particles are distributed in the other regions outside the jets, you see that in this case they tend to be distributed in this region and in this region. In this other case, in which the kinematic is the same but the color flow is different, particles will tend to be radiated in this region. And this is actually what people observe. These are, for instance, analyses performed by the Delphi collaboration. Okay. Okay, now we have to, this is more or less the end for what concerns QCD in high energy elementary collisions. Other questions? If not, let's move to, so this is a reference of some literature. This is the famous book by Ellison, Stirling, and Weber, the pink book. This is also a very nice book by this author. It is more recent, and then there are some lectures that you find online, and they are also very good. Okay, maybe we can stop for 5 minutes, okay, we can have a break. Okay, then apply the formalism that we have developed in the case of in medium propagation of a parton. So in the case in which I'm considering now, we have some hard process in which we produce some high energy parton, which rather than propagating in the vacuum and maybe emitting gluon in order to lose virtuality, they propagate in the medium. They exchange momentum and colors with the particles of the medium, and so this can induce some Bremsstrahlung radiation. So you radiate some gluon, which since have color charge, they can further rescatter in the medium. So the idea is that while in a vacuum shower you essentially radiate gluons because you have some hard event in which at the beginning you have produced some high virtuality parton, and so you radiate in order to lose virtuality. Here you are a further source of radiation, which are the color and momentum exchange with the medium. Okay. So a suddenly accelerated color charge can radiate soft gluons, like a suddenly accelerated electric charge can radiate soft photons. Okay. So the presence of a medium can be a further source of particle acceleration. Okay. and can thus enhance the probability of gluon radiation. We have a 3 elementary brick in order to evaluate this gluon radiation. The first elementary brick is this one, in which you have a scattering with some scattering centers with which you exchange a momentum q perp, and you radiate a gluon of energy omega transverse momentum k perp at an angle k perp over omega, okay? And this will be the angle which will be relevant for our for the calculations. Then you have also the possibility that you radiate after. Now, if you radiate after the scattering, you have also, if you want to be precise, it will be not always necessary, but for the moment let us try to be precise, take into account the recoil of the incoming parton. Okay, if you take into account the recoil, clearly what matters for the gluon radiation is not the angle with respect to the original direction, but the angle with respect to the direction of the radiator which has suffered a recoil. So what matters is the angle theta, which is k perp over omega as before, minus theta q, which is q perp over the energy, okay? If you do the calculation, you see that you have this structure, k perp minus x q perp over omega, okay? Where x is the energy fraction of the gluon, okay? But then in QED this would be the end. But then in QCD gluons can rescatter. So now, which is the relevant angle now? Well, the energy, the omega and k perp refer to the final state gluon, but the relevant angle is not this one, but the one at which the gluon was emitted. And so you see that since the momentum transfer is q perp, the relevant angle, and this is very important, the relevant angle entering into the calculation will be k perp minus q perp over omega, okay? So this will be everything we will need. Then we need to model somehow a medium, and in this lecture I will follow this quite elementary way of modeling a medium. I assume to have a gauge field in the axial gauge, A plus equal to 0, and arising from a collection of static scattering centers, and which they can transfer some transverse momentum q perp to my projectile. I assume that the interaction is local in this plus time, let us say, and then I have this color matrices which provide a rotation both of the projectile and of the scattering center. Okay, this is some interaction potential which I will not. I will not need necessarily to specify. If you wish, you can model it as a screened potential. For instance, like this. You remember yesterday you have seen this Debye screened potential. Okay. But it will not always be necessary to specify exactly its form, okay? It is just important that the medium is able to transfer some transverse momentum to the projectile, okay? As I said before, very often this A of Q is taken as a Debye screening potential, where this is the only place essentially in which information on the medium enters. So information on the medium enters here, which is the Debye screening mass, which is the typical squared momentum exchange in a single interaction with the medium. And the other place that in which medium information will enter will be the average transverse distance between these scattering centers, okay? Or if you wish, the average mean free path of your particle. Okay, then you will you will need to perform correctly summation over color indices with the rules that we have seen before, and in particular within this setup it will be important to consider the elastic cross-section of a projectile representation R scattering over the scattering center N in its color representation. The N is the dimension of the color representation of the scattering center. This is the square of the potential, and by integrating over the transfer momentum exchange, you get the total elastic cross section. Okay, if you put realistic numbers, a typical number for this elastic cross section is of the order of the millibarn, of a few millibarns. Okay, to be compared with around 70 millibarn, which is the total the total proton-proton cross section. So let us now consider first an ideal case. The ideal case is the situation in which you have a projectile coming from -infinity as a on-shell particle. Okay, you have a parton produced infinitely far, which now is on shell and enters into the medium and can scatter with the medium. Okay, you must evaluate the sum of these three diagram with this kinematic, where now there is also the momentum exchange Q with the medium. Okay, let us focus on the first one. Well, you see, what do I have? I have G from the interaction from the radiation vertex. TA, TA1, imagine to scatter with the particle 1 of the medium. TA, TA1 comes from this ordering of the color matrices. Then you have this usual factor for the soft gluon radiation. Then there is this factor 2p plus, which comes from the fact that I have assumed to have an iconal vertex. You remember, I decide to work within this iconal picture, so the interaction is 2p mu dot a mu. And then I have the scattering. I have this phase factor and this scattering. The color matrix referring to the rotation of the medium particle. Okay, now if you write explicitly this object, you get this result where you see here what enters is this relative angle between the radiated gluon and the parton which has suffered some recoil. Okay, so if you go back a few slides, the situation I'm considering here is this one. Okay, and in fact you see this is what enters. Evaluate also this, The only things to have to take into account is to put the correct ordering of the color matrices, and to consider the correct relative angle between the gluon and the radiator. If you do this, okay, you get for diagram B this structure in which the ordering is reversed, and in which the relative angle now is just this theta. And then finally you have this, the trigluon coming from the trigluon vertex, where actually it would contain a structure like call this color matrix TC, for instance. You would have a structure like F, A, B, C, TC, but the trick is to view this as a commutator. Okay, and so you see that if now here you neglect this subleading X corrections, The advantage is that now you can write everything is in the compact way, because here look at this difference in sign, and this you can put everything together, and for the radiation amplitude you get this result. Now again, if you want to calculate the radiation spectrum normalized to the elastic cross section for the interaction with a medium. So you want to calculate the number of gluons radiated on average as a consequence of this elastic scattering. You must normalize to the total elastic cross section. You must integrate to the phase space, take the square of the amplitude, sum of over the polarization. If you do like this, so take into account that again, once you sum over the physical polarization of these gluons, you get a factor delta ij. Okay, with this factor delta ij produce a square of this k over k perp square minus k minus q over k minus q perp square. Okay, which I decided to label as k0 and capital K1. If you perform the calculation correctly, you get this factor, where here this average means that I have taken an average over possible momentum exchange in the medium. Okay. Notice that this kernel, this dependence, is the same kernel which appears in the BFKL equation that we have seen on Tuesday, I think. Okay, you go back to the slide and you see that this dependence is exactly the same. So this is the Guignon-Birch spectrum, and it's a spectrum which refers to the case of a projectile coming from infinitely far in the past and which scatters once in a medium. Okay. Now, what one would obtain in the case of QED? Well, in the case of QED, the situation is a bit more somehow simpler, but also more subtle, because clearly in the QED case I wouldn't have this term. Okay, but notice that in the QED case, if I do this soft approximation, I have an exact cancellation of these two terms. So in the QED case, in order to consider to get a non-zero result, I must consider also these subleading corrections. Okay, and so the result is similar, but you see that I have kept this dependence on X, and so one can understand this because I mean, while the gluon of the quarks have also a color charge, so even if they don't exchange momentum, they can exchange color and be found in a different state. I mean, an electron is just an electric charge, and a photon is not is zero charge, and so it cannot rotate into some internal space. Okay, and so if I neglect the recoil, I get zero radiation. So in order to get radiation in QED, I must take into account the recoil of the charge, otherwise I would not radiate. Okay, then last consideration is that I can also take into account the fact that I have different color channels in which this object, this process can occur. So in particular, since the gluon amplitude has this structure, has this color structure, I can write explicitly this commutator and get two different color channels in which the radiation can occur. And you see, so I can attribute half of the gluon amplitude to this kind of diagram and half of the gluon amplitude to this kind of diagram from the point of view of color flow. And you have these two different color structures in which you see what's the difference. The difference may be that maybe it can be relevant at hadronization, as maybe we will explain at the end, because in this case I have radiated a gluon, but since at the end I must produce hadron starting from some color singlet object, suppose that I work in the picture in the picture in which I produce hadron starting from the string, from the breaking of some elongated string. In this case, in order to construct a color singlet string, I must join these points. So you see that the radiated gluon belongs to the same string that I'm going to fragment. While in this other case, the gluon is completely color disconnected. Okay, so it will not be part of the leading string which I will go to hadronize, but it will hadronize independently by looking for some other charges to be attached and to fragment and produce hadrons. Okay, so hadrons are in the Lund string pictures. Hadrons are imagined to be produced from the breaking of a string. You have a quark at the end point, an anti-quark at the other end point. The string gets elongated and elongated. At a certain point, it becomes possible to excite Q-cube uppers from the vacuum and produce hadrons. Okay. Okay, you can verify that if you sum the two color channel, you recover the color inclusive spectrum. Now, let us address the situation a bit less ideal, and the situation a bit less ideal is the one in which your parton is produced inside the medium. Okay, again, clearly, so what's the point? The point is that if the parton is produced not infinitely far in the past, I must take into account also vacuum radiation. Okay, so the total radiation cross-section comes in part from the vacuum radiation and in part from the genuine medium-induced radiation. Okay, the vacuum radiation comes from this process that we have already described. It means that the parton is initially produced with some virtuality and tend to get rid of its virtuality by radiating gluons. But clearly, the genuine medium-induced radiation comes from this kind of diagrams. Okay? Notice that in the case of vacuum radiation, we had this formation time, which we will see in the case of vacuum radiation was not important. We will see that in this case, first of all, it gets modified, and then secondly, it is also important because now there is a scale to which I can compare this formation time. Okay. So the recipe which I decided to follow is to perform what is called an opacity expansion. So in practice, an expansion in the number of elastic scattering which I suffer in the medium. So it is an expansion in the parameter L, which is the medium length, divided by the elastic mean free path. Okay. So I will stop at the first non-trivial order of the expansion. So the radiation amplitude comes from it can be expanded in the number of elastic interactions suffered in the medium. No interaction, one interaction, two interaction, etc. Okay? I must take the square and take an average over the medium. Okay? Notice that at the n equal to 1 order, I get a contribution from m0 square, so it's the vacuum radiation, a contribution from m1 square, so it's the square of this contribution, but I get also, at the same order, I get also an interference term between m2 and m0, okay? The physical interpretation is the following, clearly, m1 square is this one, m2 square, the interference term with, essentially the role will be to reduce the contribution of vacuum radiation, and is results from processes involving non-net color exchange with the medium. So what's the situation? I mean, I have my projectile which interact twice with the medium and can radiate a gluon, and I want to take the interference with this diagram. Now, why couldn't get also a contribution, for instance, in which I interact with two different scattering centers? Well, because if once you sum over colors, etc., see, I mean, in this case, I must take the interference in which I have not interacted with particle 1 and particle 2. So it means that I must take this color trace and this color trace. So in practice, I get a trace of TA1, but TA1 is equal to 0. Okay, so the only possibility, while on the contrary, if I interact twice with the same, I can get a non-zero result. Okay, and this is also the reason why, for instance, I don't take into account a contribution from the interference between M1 and M0, again, because trace of a single color matrix is 0. Okay, now at the end, if you do the calculation at the first non-trivial order in opacity, you get this result, where this K0 and K1 are this object which I defined here. Okay, so it is okay, and I have this coherence factor, okay, where omega 1 has the meaning of an inverse formation time. So I can distinguish two regimes: a coherent Landau, which is called, this is called Landau-Pomeranchuk-Migdal effect. Okay, this coherence effect. I can have a fully coherent regime in which in practice my formation time is much larger than the medium length. In this limit, you see this sinus over of omega 1 L divided by omega 1 L in the limit of 0. The quantity is 0, goes to 1, so 1 minus 1 is 0, and I have no medium-induced spectrum. So I have just vacuum radiation. So this suppression of medium-induced radiation due to coherence effect is called the Landau-Pomeranchuk-Migdal effect. And it was discovered in the 50s, I think, in the study of interaction of cosmic rays, I think. In the incoherent regime, vice versa, this sinus oscillates, this factor gets large, and so I can neglect this interference term. Okay? Now, let us check, let us interpret the full result in this incoherent limit. So the full result as the following must include both the vacuum result and the medium induced result. Okay, and the interpretation is the following one. I have a piece, the full result is the sum of these three terms. I have a first piece, which is the Guignon-Birch term. the one which we evaluated at the beginning. It would correspond to the radiation from a projectile which came from minus infinity. Okay, and in fact it has this structure. Then I have a term which would correspond to a sort of vacuum radiation which has simply suffered a rescattering in the medium. So I have emitted a gluon due to vacuum radiation, then this gluon suffered an elastic rescattering in the medium and is found with a different momentum. Okay, and so so the gluon, I have a off-shell object which radiate a gluon, but then this gluon suffer an elastic scattering with the medium, and this is found with momentum k perp, even if at the beginning was produced with momentum k perp minus q perp. Okay, but it is still a vacuum radiation. It is the projectile which is off shell and radiate a gluon. The gluon has a color charge and suffer a vacuum radiation. And then I have finally this term which is simply the vacuum radiation, this one, and then a minus, so a term in which I subtract the gluons which were produced with momentum k, but then due to interaction with the medium were no longer found with momentum k perp. Okay, and so of course once you see that once you integrate over all phase space of the radiated gluons, these two term cancels. Okay, and okay, that's all. Now let us focus on the medium induced part. Okay, this is just to justify the fact that you have this difference in deformation time, that rather than having simply 2 omega over k square, you have this expression in the n equal to 1 opacity expansion. Now, what is which are the properties of the radiation of the radiated spectrum of radiated gluons? Well, at variance with respect to the vacuum radiation, the spectrum is both infrared and collinear safe. So if you study its limit for omega going to 0 or for theta going to 0, you get a finite result. These are curves which were obtained with some realistic numbers for a Rick collision, so an energy of the initial part of 10 GeV, a medium length of 5 Fermi, a Debye mass of alpha GeV, a mean free path of 1 Fermi, alpha S 0.3. Okay, if you want to be precise. Notice that you can also decide to integrate the spectrum or all possible momentum fraction, and what you get is that in general this average number of radiated gluon is larger than 1. So the point is that addressing multiple gluon emission becomes mandatory. Okay. You can also integrate the spectrum, and you get in the limit of a very highly energetic parton. After integration, you get this result in which you see you have a dependence on alpha S, a dependence on the color charge of the projectile. A gluon radiates more than a quark. A dependence on L square, which comes from this interference effect, from this coherence effect. Otherwise, you would get a dependence on L. And then you have, notably, this dependence, the Debye mass square over the elastic mean free path. Now, since the Debye mass is the typical square momentum exchange in a single collision, this can be considered as a transport coefficient, and it is often called Q hat, and in practice it is the average transverse momentum squared acquired by the projectile per unit length in the medium. Okay, and so this formula is very often very appreciated by the experimentalist, and which they always quote, even in context in which it is not so precise and justified to quote it, but it is very convenient because it is very easy to remember and to interpret. Okay. Notice, so the important point that I would like to stress is that the average energy loss is independent from the energy. Okay, it does not depend asymptotically for very high energy of the projectile. The average energy loss no longer depends on the energy, and we will see whether that this will help us in interpreting the experimental data. Okay, as I was saying, people had to somehow face this issue that on average you radiate more than one gluon, and also the issue that since everything was disconvoluted with a spectrum which is strictly falling, the knowledge of this expectation value of delta E is not sufficient to characterize the quenching, but you must really know the whole probability distribution of energy loss, not simply its lowest order moment. And so clearly, so far we have simply evaluated the inclusive single particle spectrum in practice. We have seen from the study of vacuum radiation that successive gluon emissions are not independent, because at least in the vacuum you have this angular ordering of the radiation, you have these coherence effects. So I mean, the situation is a bit tricky, but okay, at the beginning people tried the simplest approach and to take the successive emissions as independent, and describe them with this sort of Poissonian distribution, okay, in which the integration of the single inclusive gluon spectrum is used to estimate this average value of radiated gluons, and you get this probability just imposing the energy conservation, okay, for coming from the sum of all the various gluon radiation. If you do like this, I mean, you can attempt to reproduce the experimental data starting from some initial condition for your medium. So these are quite old results, which now maybe they are more recent and with better agreement also with the experimental data. Okay, now let us try to end with some heuristic estimate for the relevant kinematic of medium-induced gluon radiation. Okay, so formulas have been derived in the opacity expansion and then equal 1 order for simplicity. Now let us move to the opposite limit, in which I assume that I have a thick medium in which I interact many times. Okay, so we have seen that the formation time of the gluon has this expression with this dependence also on the transverse momentum exchange with the medium. Now, in the limit in which the gluon interact, the parton interact many times, this Q comes from the sum of all these interactions. Now, in the limit in which these interactions are there are a large number of interactions, we can imagine that in the square, first of all, this is dominant with respect to this, and then I can imagine to have a sort of a random walk, so that the square of this sum is simply the number of the scattering centers times the average Q square exchange in a single collision. Okay. Now, which is the number of scattering which I suffered in the medium during the time which was required to radiate a gluon. Well, this number is nothing but the formation time of this radiated gluon divided by the elastic mean free path of the gluon. Okay. Now you see that now you can put this formation time or formation length here, and you get as a result that the formation time of your gluon is the square root of omega over q perp. Q perp is a transport coefficient. So you see that you have a very different situation with respect to the vacuum, because the formation time in the vacuum was of order 1 over omega theta square. So soft gluons are emitted very late, while here the formation time in the medium is of order omega over q perp. So soft gluons are emitted earlier. Okay? So this is a qualitative difference. Now let us put some number. Remember that h bar c is equal to 0.2 GeV times Fermi. So it means that 1 GeV times Fermi is a number of order 5. No, now gluon radiation, as we have seen, is suppressed if the formation time of the gluon, formation time which depends on the frequency of the energy of the gluon, is larger than the length of the medium. Okay, and this occurs above a critical frequency. Okay, so from this condition that the formation time, which is the square root of omega over q perp, must be smaller than L, I get this condition for the energy of the radiated gluon. So it means that above this value, gluon radiation is strongly suppressed. Of course, I expect that the spectrum will decrease in any case, but on top of the simple kinematic suppression, I get this further suppression due to coherence effects. Okay, if you put a realistic number for this Q8, which is of order a few GeV square per Fermi, and a medium length of around 5 Fermi, you get this something like this. Okay, and you can also estimate the typical angle at which gluons are radiated. So the K perp square of the gluon should be equal to Q8, which is the transverse momentum squared per unit length, times the formation time of this gluon, and you see that you get this from the expression for the formation time, you get this result, and if you substitute, you get this dependence. So in practice, softer gluons tend to be radiated at larger angles. Okay, the softer the gluon, the larger the angle at which it will be radiated. For instance, for Q8 1 GeV square per Fermi, you see that a 2 GeV gluon can be radiated at theta equal 0.4. A 5 GeV gluon tend to be more collinear. Okay, so soft gluons can be radiated at larger angles. Now consider that once you reconstruct jets in heavy ion, usually you use jet radii of order 0.3. Okay, so for instance, a gluon of energy or radiated at an angle 0.4 is already outside the cone of the jet that you study. Okay. So on the other end, below another critical frequency, which caused Bethe-Heitler frequencies, I mean, if the deformation time of the gluon is smaller then the elastic mean free path, I have no longer any coherence effects because successive gluon emissions can be treated as incoherent, okay? Because it is like having many independent radiators, okay? And coherence effects should be no longer important. So this critical frequency clearly is much it is much smaller because instead of having L squared, where L is the length of the medium, here I have the elastic mean free path. Now I can estimate the spectrum of radiated gluon in this coherent regime, and what one has to do is simply to express the medium thickness in units of the gluon formation time, okay? So clearly in the case of incoherent emission, here I would have a dependence just on L, okay? But in the case of coherent emission, this medium length must be measured in units of the formation time of the gluons, okay? Because I mean, in the incoherent situation, this L would just count the average number of independent radiators. But if I have coherence effects, I must actually measure this length, taking into account the fact that I have a finite formation time, which usually is larger than the elastic mean free path of the projectile. If I insert the expression for this formation time, I get this expression for the gluon spectrum, which now I can integrate over omega and weighting it by the energy of the radiated gluon, and this allows me to estimate the average energy loss by integrating the spectrum between these two critical frequencies. Clearly, the lower limit can be set to 0 if since this is much larger than this, and as you can see, you get from the integration of this 1 over square root this expression, which now if you put the definition, this definition of omega critical, you get, you see, this dependence. So it's the result that we have seen before. It's alpha s, the color charge of the projectile, q hat, this transport coefficient, times L square, arising from this coherence effect. So we have recovered on a heuristic basis the formula of before. Formula which, I stress, turns out to be independent on the energy of the projectile, okay? Or at least with a weak dependence. So let us check whether all this stuff help us in understanding the experimental data. Yeah, well, I would say probably yes, because you see the RAA which has this rise, which was discovered just at LHC, because at RIC, I mean, at RIC one stop the many years ago, one could only consider transverse momentum up to 10 GeV, and you were seeing just this plateau, but around this minimum. But at LHC, where now people can go up to much higher PT, one discovers this rise in the RAA that probably one could interpret as being due to the fact that asymptotically this energy at this average energy loss has a very mild dependence on the momentum. So it's not that I lose a finite fraction of energy. I lose a finite quantity of energy. Okay. And now, and the people is also interested now in really performing differential jet studies and looking where the radiating energy goes. So for instance, this is a study of jet shapes. So one consider a digest event with a leading and a subleading jet, and so one identify a jet axis, and one can also identify rings around this jet axis and look at the energy fraction of the jet in each of these rings at a given distance from the jet axis. Okay, and one can also study the tracks, so the transverse momentum of the particles belonging to the jet as a function of their distance from the jet axis. So you see here you have the density of energy in a given of jet energy, the fraction of jet energy in a given ring at a distance delta r, and here beside the total result you have also how this result comes from the contribution of different particles, from soft particles to hard particles. So particles with pt less than 1 GeV, particle with pt larger than 8 GeV. You see, this is the situation in proton-proton. This is the reference measurement at the same center of mass energy, and this is the situation in nucleus, in peripheral and central event. And for instance, look at central event. You see that you have a large enhancement of energy fraction away from the jet axis, very far from the jet axis. You see that these jets were reconstructed with anti-KT algorithm, which is the name of the jet finding algorithm, and the jet radius was taken as a 0.3. So you see that 0.3 is here, and you see that in nucleus you have a lot of energy outside this jet, and a lot of energy which is carried by soft particles. Okay, because in violet you have soft particles. Okay, and this was for the leading jet, and this is the same study for the subleading jet. Okay, and again, the fact that softer particles are radiated at large angles nicely fits with, you see, here soft particles are more concentrated at the small values of R, while here soft particles extend to much larger values of R, which I would say is consistent with this picture in which the softer the particle, the average, the larger the angle at which it is radiated. Okay, then I would end just with some considerations about possible effects at hadronization due to this modification of color flow. Okay, as I said at the beginning, let us consider how you go from partons to hadrons. So this is an example of a plus minus event in which you produce a Q-cube pair which radiates some gluons, and maybe one of these gluons splits into a Q-cube pair, and then you must hadronize. Okay, at a certain point particles goes almost have a so small virtuality, then I have to make the transition from partons to hadrons. So I must start looking for some color singlet object, which then I will hadronize. Okay, so here in this figure I recognize two color singlet object, which I can define as strings stretched between. This is a quark, and this is an anti-quark as the opposite endpoint, and this is another string with a quark and an anti-quark as endpoints. So the picture is the one that I discovered, which I told you before. Well, the motion of this string would be some yo-yo motion. Okay, But from time to time, once the string is stretched very much, it can becomes convenient to excite some q-cube pair from the vacuum, and so from one string you go to string, and then you can fragment the process can be repeated, and you have so at a certain point you have hadrons. Okay. Now this is the situation. This is how Pitya would describe. This is how the same thing would be described by Herwig. The difference is that Herwig forces at the end of the shower each gluon to split into a q-cube pair, and so you have a larger number of color singlet cluster to hadronize. But again, the idea is that you have some color singlet object which must hadronize into hadrons. Okay. So what would happen in an elementary collision? Okay, suppose here I have written a nucleus, but you consider it a proton. Okay, I model some hadron. I model two hadrons as two opposite color charges. There is a hard process. After the hard process, I can have some radiation, and then I must construct a color singlet object to hadronize. And in this case, in this very schematic cartoon, the only color singlet object can be constructed by attaching this gluon to the beam remnant. Okay, and then you have this string that you must hadronize. Okay. Now, what happens in the case in which you have also a medium? Well, in the case of in which you have also a medium, at the point the situation is different, because now we have a medium which is some color, some reservoir with which you can exchange besides momentum also color. So you can radiate gluons, and then now you can look how these gluons that you have radiated are color connected, and you see that depending on the color channel in which this scattering, this radiation take place, you can have different color structures, which can lead to effects at hadronization, because in this case the gluon is radiated, is attached to the radiator. In this other case, the radiated gluon is no longer attached to the leading parton, which has lost some energy and must be hadronized independently. Okay, with an independent string. So this is just a sketch of what you would get by studying the fragmentation of these two different configurations. And in the green case, you see you have a depletion of hard particles and an enhancement of soft particles from the hadronization of this subleading string. So, I mean, the point is that kinematic is the same. Maybe that these two gluons are even radiated with the same probability, but I mean, the color flow can change the way you go from partons to hadrons. Okay, this is just some ideas for future investigation. Okay, here I have collected some reference that you can also look at, and I think we can stop here. Okay, if there are questions. No question.